In our previous lecture, we reviewed Laplace transform. Okay, we started with its definitions and we discovered certain consequences of that definition, as well as obtaining certain f of t, f of s pairs. In particular, for certain types of f of t, time domain signals, we, using the definition of Laplace transform, obtained the f of s, s-domain representation of that time domain signal. Okay, and today what we will do is we're gonna obtain the time domain representation for a given s-domain signal. Okay, so for a given f of s, we will try to obtain the f of t. Now, the types of s-domain signals, or the types of f functions, will be such that they have the form of a ratio of two polynomials, okay, in S. So, and when you have such a form, especially for signal processing studies, it's beneficial to also represent that f of s more visually on a complex plane, and that representation is called the pole zero diagram. Okay, so we begin this lecture by introducing what we mean by a pole zero diagram, and then we will move on to studying the transformation from Laplace domain to time domain over some simple examples. Okay. Pole zero diagram. So we will be interested in signals, okay, whose Laplace transforms have the following form. Okay, f of s equals some polynomial of s divided by some other polynomial of s, okay, where the polynomial coefficients are all real. So let's write the numerator polynomial first, b 1s m minus 1 bm minus 1s plus bm. Okay, so here we have an mth order polynomial if b0 is different than 0, and then for the denominator we can write sn a1 sn minus 1 an minus 1s plus an. Where the coefficients, namely all a's and b's, are real numbers, where ai, bi are real numbers. Okay, now expressed in factorized form, this ratio can be written as follows, and by factorized form we mean the following. This is an nth order polynomial, therefore it will have n roots. This is an mth order polynomial, it will have m roots, therefore this polynomial can be written as product of n first order polynomials. Okay, likewise this can be written as a product of n first order polynomials, and if you write f of s in that form, that's called the factorized form. Okay, so f of s can be rewritten as k times, suppose we somehow computed the roots, which is not an easy task if the polynomial is of order 3 or larger, so you can always take software help. But somehow, suppose we obtain those roots and write f of s as the product of these m first order terms divided by the product of these n first order terms, s minus pn. Okay, and this k is called the scaling factor, and if you compare this to ratios, since they're representing the same function f, k must be b0. Okay, where k b0 is called the scale factor. Okay. Now, these n numbers, namely the roots of the denominator, they're important both in inverse Laplace transform calculations and also in some other places. Also, zeros have importance too. These roots have importance too. Therefore, they're given some special names. Okay, in particular, the roots of the denominator polynomial are called the poles of the function f, and the roots of the numerator polynomial, they're called the zeros. Okay, denominator roots namely these n numbers. Okay, note that we're dealing with polynomials with real coefficients. Therefore, even though we may have complex roots, those roots always appear, if we have a complex root, they always appear as complex conjugate pairs. Okay, now these denominator roots are called poles. Okay, and the numerator roots z1, z2, zn are called zeros of f of s, or if you know the time domain signal, you can also say they are the zeros of f of t. Okay, now let's apply this definition to a simple example. Okay, find the poles and zeros of the following given time domain signal. Find the poles and zeros of f of t given as e to the minus 2t plus cosine 2t minus sine 2t. Okay. Now, where the poles should be on complex plane are almost obvious by looking at f of t, but to see the zeros clearly, we have to obtain f of s and write it as this form. Okay, so let's do that. We have to obtain the Laplace transform of f of t. In other words, we have to obtain f of s. Now, f of t contains three terms. By using the linearity property of Laplace transformation, what we can do is we can obtain the Laplace transforms of each of those terms separately, and then we can combine them, okay, because transformation is linear. And those three pieces we already obtained in our previous lecture. We already know their Laplace transforms. Okay, so f of s can be written as, therefore, the sum of three Laplace transforms. Laplace transform of this, Laplace transform of cosine 2t, and Laplace transform of minus sine 2t. Now, Laplace transform of this exponential function is 1 over s plus 2. And we have cosine term here. Laplace transform of cosine omega t was s over s squared plus omega squared. In this case, omega is 2. Therefore, we have s over s squared plus 2 squared, okay, which is 4. And for Laplace transform of sine omega t, we know that it equals omega over s squared plus omega squared. Therefore, we have 2 over s squared plus 2 squared. Okay, now that equals 1 over s plus 2 plus s minus 2 s squared plus 4. And going one step further, we can write this as s squared plus 4 plus s squared minus 4 over s plus 2 times s squared plus 4. Okay, and that equals, we have 2s squared for the numerator, so we put the 2 here, that's our scale factor, and then here what remains in numerator is s squared. As for the denominator, we have s plus 2, it's already in first order term form, and then this second order term we have to express as the product of 2 first order terms, and that's easy because it's simply s plus j2 times s minus j2. Okay, so this is in now factorized form, therefore we can easily spot all the poles and zeros of f of s, or equivalently all the poles and zeros of f of t. Now if you mark those poles and zeros on the complex plane, what you obtain is called the pole zero diagram of f of s, or pole zero diagram of f of t. Okay, so the poles of f of t or f of s are at, we have a third order denominator polynomial, so that makes 3 roots, so that makes 3 poles. One of the poles is real and it's at -2, and then the remaining 2 poles are on the imaginary axis at location j2 and minus j2. Note that they are the complex conjugates of each other, which they must, because we deal with a real coefficient polynomial. So the poles are at -2, minus j2 and j2. And as for zeros, the roots of that polynomial, s squared, are both at 2. Okay, so we have 0 and another 0 for the root of the numerator polynomial. So those are our zeros. Okay. Repeated zeros at the origin. Okay. Now finally what we do is we express this information together with the scale factor on the complex plane. So how that's done is, conventionally, the poles are marked with little crosses and the zeros are marked with tiny circles. Okay, and somewhere on the picture you write the scale factor. Okay, k equals 2. Okay, so this is our imaginary axis, this is our real axis. This is the origin, and this is our complex plane. Okay, so what we have here is -2 as one of our poles. Okay, and j2 and minus j2 as our remaining poles. So those are the poles. A pole in a pole zero diagram is represented by a cross. Pole is denoted by x, and 0 is denoted by a tiny circle. Okay, so when you have a 0 that's repeated, what you do is you draw concentric circles to indicate that you have two zeros at the origin. Okay, and somewhere on the picture we have to indicate the scale factor, and now this picture contains all the information that's contained by this f of s. Okay, so therefore it's another representation, and sometimes this representation, because it's more visual, it's more beneficial for certain types of analysis, okay, related to signal processing. Okay, so having defined pole zero diagram, now we can move on to the inverse Laplace transform. Inverse Laplace transform. Note that when we obtain the Laplace transforms of certain time domain signals, f of t, what we did is we used the definition of Laplace transform, okay, which takes f of t and produces f of s, which was an integral computed from 0 to infinity. We use that definition and sometimes certain properties of the Laplace transform to obtain f of s. Now, for a given f of s, there's also an integral definition which takes f of s to f of t, but we're not going to use that definition. Instead, we will go in the following way. Okay. So first of all, this is our problem for a given f of s, okay, which will always be in the form some polynomial dividing by some other polynomial. We're going to find the signal, the corresponding signal in time domain. Okay, so let f of s be b0 as m plus b1 as m minus 1 plus bn divided by the denominator polynomial a1 as n minus 1 an. Okay, and b0 is different than 0, so that the numerator polynomial is of order n and the denominator polynomial is of order n. If degree of denominator polynomial is strictly larger than degree of numerator polynomial, then such transfer function is called a proper. Okay, then f of s is called a proper rational function. Okay. Now, let's begin by the simplest case, where we have poles that are not repeated. Okay, and then we're going to move on to the general case for repeated poles. Okay, special case. The case of so-called simple poles. Remember that by pole we mean the roots of the denominator polynomial. So that's what we just defined. If the denominator polynomial of f of s has no repeated roots, then that f, okay, f of s, is said to have simple poles. Okay. Okay. That is, we can write f of s in factorized form as follows: b0sm plus b1sm minus 1 bm divided by s minus p1 s minus p2 s minus pn. Okay, we have n poles because the order of the denominator polynomial is n, and for the simple pole case the situation is such that no two poles are the same. Okay, in other words, pi is different than pj whenever I is different than j. Okay, now suppose that we're given an f of s that's proper and the poles are simple. Okay, so let f be a proper rational function with simple poles. It is no poles are repeated with simple poles. Then we can write f of s as sum of n first order rational functions. First order proper rational functions. So we can write f of s equals k1s minus p1 plus k2s minus p2 plus kns minus pn. Okay. Now these scalars, possibly complex, that appear in the numerators are called residues. Okay. And k, for instance, k2 is the residue for the second pole, and so on. Okay. The ki's associated with each pole are called the residues. Okay, here's another definition. Now, how do we compute those residues? First of all, it's more or less clear why, if you want to obtain f of t for a given f of s, why we want to express f of s in terms of sum of n first order terms. In other words, why we want to figure out k1, k2 up to kn. The reason is simple, because if somehow we can write f of s in this form, we can easily obtain the inverse Laplace transforms of these first order terms. Namely, this will yield k1 times e to the p1t in time domain, and this is k2 times e to the p2t, and so on. And since transformation is linear, the Laplace transform of this guy, inverse Laplace transform of this guy, equals the sum of inverse Laplace transforms of each of these simple first order terms. Okay. So therefore, this step is very important. That is, going from a single ratio to n simple ratios is important for inverse Laplace transform operation. Okay. Now, it's not difficult to see, and I will try to convince you why that is the case. Perhaps you already see it in the following example, that ki, the ith residue corresponding to pi, equals s minus pi times f of s, and then you evaluate this at s equals pi. okay, which directly follows from this being equal to f of s, or this being equal to that. But still, I will put a y here for you to think about. Okay, now let's apply this to an f of s in our next example, and then by doing that we will be able to obtain f of t for a given f of s. Okay, now our first example, where we have a proper rational function with simple poles. Furthermore, the poles are all real. So this is the simplest possible case, more or less. Let f of s be given as 2s plus 6 over s cubed plus 3s squared plus 2s. Okay, so that's our f of s. It's called third order because the degree of the denominator polynomial is 3. Now, we want to obtain f of t corresponding to this f of s. So what we're going to do is, first we will write this f of s, if we can, as sum of 3y3, because the degree is 3, the order is 3. Sum of 3 first order terms, and then once we do that, it will be really easy to obtain the inverse Laplace transform, because once we have this form, we know the inverse Laplace transforms of those guys. Okay, so this equals 2s plus 6 over, it's clear that we have a pole at 0, and the remaining poles are at -1 and -2. And we have a 0 at -3. Now, this equals, because it has simple poles and it's proper f of s, this f of s can be written as sum of 3 first order terms. Namely, we have to have, for some k1, k2 and k3, f of s equals k1 over s plus k2 over s plus 1 plus k3 over s plus 2. Okay, now the question of course is, what is k1, k2 and k3? And the answer is here. Okay, now this, so what we want to do is we want to figure out k1, k2 and k3. This we know equals that, or this, okay? So we know what this is, all the coefficients are there, but we don't know what k1, k2 and k3 are. So suppose that we want to figure out k1. First multiply both sides with the denominator of k1, which is s. If you do that, what you obtain is k1 plus k2s over s plus 1 plus k3s over s plus 2. So what we did is we multiplied both sides, this is f of s, with s. Okay, this term will be sk1 over s, and those s's will cancel, and we will be left with k1 sitting on its own. And this equals what? That equals s times f of s. Okay, now if you want to compute k1, what we can do is we can evaluate this at s equals 0. Okay, and because we're evaluating it s equals 0, all these terms, we don't have to know what k2 and k3 is, because they will be cancelled by this 0 here, and then this whole thing will become equal to k1. Okay, now since both sides are equal, this thing k1, okay, Okay. Okay, must equal s times f of s evaluated at s equals 0. Now, what's s times f of s? This is our f of s. Okay, we multiply it by s, and what we have is 2s plus 6 times s divided by this. Now, s in the numerator will be cancelled by s in the denominator, and this thing here, s times f of s, equals 2s plus 6 over s plus 1 times s plus 2. Therefore, K1 must equal this expression evaluated at s equals 0. Okay, which is 6 over 2, 3. Okay, now likewise, K2 equals, what's the denominator of K2? It's s plus 1, so s plus 1 times f of s evaluated at s equals what? Evaluated at the value of s, which makes this denominator 0. Okay, in other words, s equals minus 1. So multiply this with s plus 1, and then that s plus 1 will cancel with s plus 1 in the denominator. So we have 2s plus 6 over s times s plus 2, and then we evaluate this at s equals minus 1, and that will give us K2. 4 over minus 1, that's minus 4. And likewise, K3 is s plus 2 times f of s evaluated at s equals minus 2, and that gives us K3 equals 1. Okay, so now we know K1, K2, and K3. K1 is 3, K2 is minus 4, and finally K3 is 1. So we can write f of s equals 3 over s minus 4 over s plus 1 plus 1 over s plus 2. And once written in that form, it's very easy to compute f of t. F of s equals K1 over s plus K2 over s plus 1 and plus K3 over s plus 2. Then f of t is the inverse Laplace transform of f of s, which equals, thanks to the linearity property or linearity of the transformation, this is 3 times inverse Laplace transform of 1 of s minus 4 times the inverse Laplace transform of 1 over s plus 1, and finally plus inverse Laplace transform of 1 over s plus 2. Now that we immediately recognize those inverse Laplace transforms, this will give us a constant term. Okay, 3. This gives us the exponential term e to the minus t. And finally, this gives us another exponential term, e to the minus 2t. Okay. Therefore, this is the inverse Laplace transform of 2s plus 6 over that denominator. Okay, now let's see another example, again with simple pole case, but this time we allow the poles to be complex. Okay, our next example reads as follows. Okay, f of s equals 20s plus 3 over s plus 1 times the second order term, s squared plus 2s plus 5. Okay. Now, here we have a second order polynomial, and it will have two roots. It turns out that those roots are complex. It's not difficult to see that. We can rewrite this as 20s plus 3 s plus 1 times s plus 1 plus j2 and s plus 1 minus j2. Okay. Again, we have no repetition of the poles, therefore this is a proper rational function with simple poles. So that means f of s can be written as k1 over s minus p1 plus k2 over s minus p2 and so on. k1 over s plus 1 plus k2 over s plus 1 plus j2 plus k3 over s plus 1 minus j2. Okay. Now the procedure applies equally well to the case where you have complex poles. Okay. Therefore, it's easy to compute k1, k2, and k3. But we expect some complex. Previously, they were all real because the poles were real. But this time, we expect certain complex numbers as our residues. Okay. So let's begin with k1. k1 is s plus 1 times f of s evaluated at the value of s, which makes the denominator 0. That is evaluated at s equals minus 1. S equals minus 1. So that's 20s plus 3 over s squared plus 2s plus 5. Because if you multiply f of s with s plus 1, this will cancel the s plus 1 sitting at the denominator, and you are left with this expression. And what we do is we evaluate that at s equals minus 1, and that yields 40 over 4, 10. Okay, so we have figured out k1. So we know that f of t will be 10 times e to the minus t plus some other terms. Okay, how about k2 and k3? k2 equals s plus 1 plus j2 times f of s evaluated at s equals minus 1 minus j2. Okay, so that equals what? If you multiply f of s with s plus 1 plus j2, this term will cancel the same term in the denominator, and what remains is 20s plus 3 over s plus 1 times s plus 1 minus j2, and then you evaluate this at minus 1 minus j2, and that yields minus 5, 1 minus j after some simplification. And finally, k3 equals s plus 1 minus j2 times f of s evaluated at s minus 1 plus j2. That equals 20s plus 3 s plus 1 times s plus 1 plus j2 evaluated at s equals minus 1 plus j2, and that turns out to be minus 5, 1 plus j. Okay. Now, note that k2 and k3, if you look at them, they satisfy an important relation. They look very similar to one another, except that here we have minus j, here we have plus j. Okay, and that means k2 and k3 are complex conjugates of each other. So that's not a coincidence. The reason is that they are the residues corresponding to complex conjugate pair of poles. So that means, since we'll always be working with real valued, real coefficient polynomials, so once you computed k2, you don't have to compute k3, because k3 must automatically be complex conjugate of K2. So let's put that remark down because it can be time saving. Okay, note that K3 is the complex conjugate of K2. Okay, this notation means complex conjugate of K2. This is not a coincidence. Because residues of complex conjugate poles are complex conjugates of one another. Poles are complex conjugates of each other. Okay, and this is because f of s has real coefficients, or only real coefficients. Okay, now we're ready to write down f of t, because we now have the expression of f of s in terms of sum of first order terms, and first order terms are very easy, straightforward to deal with. Okay, f of s equals 10 over s plus 1 minus 1 minus j s plus 1 plus j2 minus 1 plus j s plus 1 minus j2. That means f of t equals the Laplace transform of the first term, which is 10 e to the minus t, minus 5 minus j times Laplace transform of 1 over s plus 1 plus j2, and that's e to the minus 1 plus j2t. Okay, and finally, for the last term, we have plus j e to the minus 1 plus j2, excuse me, 1 minus j2 t. Okay. Now, formally speaking, we're done. We obtain f of t, time domain signal, for the given f of s. But usually this is not where we stop, because we know that f of t is a real valued function, but this expression contains some complex numbers. So let's try to get rid of those complex numbers and find a prettier form for f of t. Okay, so let us write f of t in a prettier form. Okay, by which we mean we will try to now get rid of those complex numbers. So for that, it turns out that it's beneficial to express the coefficients of these complex exponentials in polar form. Okay, this is given in rectangular form. Now we'll try to express them in polar form. Now, for that, we have to make the following observation. We have here minus 5 plus j5. Okay, and we want to write this as the radius or the magnitude r times e to the j theta, where theta is the argument or the phase. What's the r and the phase? For that, let's somewhere quickly draw or express this number, minus 5 plus j5, on the complex plane as a vector. When we do that, we're gonna see immediately what the magnitude should be and what the phase should be. So this is our complex plane, real, imaginary. This is the origin. Now this is our complex number. Its real part is minus 5. Therefore, the projection of it on the real axis is minus 5. Okay, so the coordinates is minus 5, and for the imaginary part it's J5. So we have here J5, and our vector is this point. Okay, this is minus 5. So let's draw it as a vector. Okay, this is our minus 5 plus J5. Now, here this is 5, this is 5, therefore the angle here is 45 degrees. Okay, 5, 5, therefore the hypotenuse is 5 times square root of 2. Therefore, the radius of our complex number in polar coordinates, polar representation, is 5 times square root of 2. How about the theta? How about the angle? We measure by convention the angle starting from the positive horizontal axis and going in counterclockwise direction. So we're talking about this here, which is 135 degrees, because this here is 45 degrees. Okay, so we have therefore 3 pi over 4 radians as the phase of this complex number. In other words, we can express this as the radius, the magnitude, times e to the j 3 pi over 4. Okay, and likewise minus 5 minus J5, its complex conjugate has the same magnitude as it should, and the phase is minus J 3 pi over 4. Okay. Now let's replace these two coefficients with their polar representations, and then that will allow us to write f of t where there are no real coefficients, there are no complex coefficients. Okay, so f of t equals 10 e to the minus t, and then plus 5 square root of 2 times e to the j 3 pi over 4 times e to the minus 1 plus j to t, and that can be written as further plus 5 square root of 2 e to the minus t, and then e to the minus j 2t minus 3 pi over 4. Okay, and likewise the other term will be the complex conjugate of this, 5 square root of 2 e to the minus t, and then e to the plus j 2t minus 3 pi over 4. Okay, that equals what? 10 e to the minus t plus 5 square root of 2 e to the minus t, and here we have the same term in the next piece, and therefore this is e to the minus j 2t minus 3 pi over 4 plus e to the j 2t minus 3 pi over 4. Okay, and then we use the relation between complex exponential and sinusoidal functions, namely here we have e to the minus j theta plus e to the j theta, and that equals 2 times cosine theta, theta being this thing here. Okay, 2 times cosine 2t minus 135 degrees. Therefore, the f of t that we have written down must equal to this real function, 10 square root of 2 e to the minus t cosine 2t minus 3 pi over 4 radians.